Now let's look at a couple slightly more complicated examples and see if we can figure out the radius of convergence and the interval of convergence for these power series. And so the first one is the sum of x to the n over n. And typically for power series, the easiest test to use to figure out which values of x it converges for is the ratio test. And so I'm going to take the limit as n goes to infinity of this absolute value of the n plus first term, so that's x to the n plus 1 over n plus 1, times the reciprocal of the nth term, and so that would be n over x to the n. And then again, just like usual, I'm going to rewrite this so that like terms are next to each other, and so this would give me an x to the n plus 1 over x to the n times n over n plus 1. And now I need to figure out what this limit is as n goes to infinity. And so first of all, this expression right here can simplify just to an x because most of the x's cancel between the numerator and the denominator. And then for this term right here, the leading terms match. And so this tends to 1. And so if I combine both of those facts together, then I can see that this limit is going to be just equal to the absolute value of x. And then the ratio test says that this will converge if it's less than 1. And so we also know that if it's greater than 1, then it's going to diverge. So that tells me most of the possible values for when this converges or diverges, because now I know if x is between -1 and 1, it converges, and if x is outside of that range, then it diverges. But there's the problem that the ratio test is inconclusive if x, the absolute value of x, is equal to 1. And so I still need to check those two cases, and that'll be a constant theme for checking for convergence of power series, is that after you apply the ratio test, you still need to check endpoints. And so I'm calling these endpoints because they're at the end of the interval of convergence. And so what I'm going to do is I'm going to plug in the two values where the absolute value of x is equal to 1. And so that's x is equal to -1 or +1. And so if I plug in x equals -1 into my series, then it becomes the series -1 to the n over n. And this series converges by the alternating series test, since 1 over n is a function that decreases down to 0. The other series, when I plug in x equals 1, that's the sum of 1 over n, because 1 to the n is always just 1. And this one diverges by the p-test. And so now we've checked every possible value of x and seen whether or not it converges or not. And so in this case, the interval of convergence, or the range of values where this series does converge, that's going to be -1 included up to a +1 that's not included. And then I also want to report the radius of convergence. And here, again, the idea is going to be that I want to look for this simplified statement where I found that the absolute value of x is less than something. On the right-hand side, that's just equal to a 1. And so the the radius of convergence is going to be 1. It is the case that the radius of convergence will always end up being half the width of the interval of convergence. And typically when you use the word radius, you think about circles and the length of the circle, or of the length of the line from the center of the circle to the edge of the circle. And it really is the case that even though it might not seem like it, this word radius is coming from circles if you view things in complex numbers. And so if you're willing to draw things in the complex plane with a real axis and an imaginary axis, then the region where a power series converges really is a circle. And so that's where it gets its name, but for us, we're never going to see the full circle because we'll only look at real numbers. All right, one more example here where we have the sum of n factorial times x to the n. And so you might be able to make a prediction for which values this converges. N factorial is very, very large. In fact, it's larger than any exponential. And so the guess should be, it doesn't matter what the value of x is, n factorial is going to dominate. And so overall, this should probably diverge for essentially every value of x. I'm going to use the ratio test to show that that's actually what happens. And so here we're going to take the limit, again, of the ratio of consecutive terms with those absolute values. And so we'll have n plus 1 factorial times x to the n plus 1 divided by n factorial times x to the n. And so in this one, there's no rewriting to be done. Things are already next to their appropriate terms. And so the n plus 1 factorial over n factorial, that'll just simplify to an n plus 1 because everything else in the n plus 1 factorial just cancels. And then the x to the n plus 1 divided by x to the n, that just simplifies to x. Okay, and so now we need to take the limit as n goes to infinity, where x is just some constant. And so this is a little bit weird because you might be tempted to say, well, as n goes to infinity, this entire thing goes to infinity. Turns out that that's not quite true because it does depend on the value of x a little bit. And there's really 3 different cases where this limit is going to be infinity or minus infinity. And you could tell that that matters because either it's going to be a positive number if x is positive, or it's going to be a negative number if x is negative. And then there's that one borderline case where x is just 0. And if x is 0, then you can see that this term inside here is always equal to 0, no matter what n is. And so actually the limit in that case is just 0. And so now we can see what happens in each of these cases according to the ratio test. The ratio test says that this limit would have to be less than 1 in order for it to converge, and that does happen, but only in this one case. And so that's telling me that the interval of convergence is going to look a little bit dumb, but it's just the interval from 0 to 0, including 0, because it does converge there. And then in this case, the radius of convergence, or in other words, the width for which this converges, is just going to be 0. And I could see that that would be true because another way of rewriting this line right here, or this limit expression, would be to say that I needed the absolute value of x to be less than or equal to 0 in order for this to converge. And so the 0 is on the right-hand side again.